you have some insulator material, semiconductor material, and you have some source and drain. Source and drain, and again some conductor material. Bottom is shown as a printed, bottom figure is your printed thin film transistor. Now this conductor material widely used in printed technology is silver, and you have a carbon, you have some aluminum also, some organic conductor as well, polypyrrole, polyamylene, then P.PSS. These are the common organic material that is used as a conductor. Then you have a nanoparticles, gold, silver, copper, nickel, carbon nanotubes. Now nanowires is also nowadays is very popular. The small wires in nano dimension. Then graphene. Graphene is nowadays widely used in these technology. For insulator, you have metal oxide, nitrates, polymer dielectrics, for example, PVP or PMMA. These are the organic dielectric used for the electronic device. And you have a semiconductor, organic semiconductor. You have oxide semiconductors, carbon nanotubes in some form is also used as semiconductor nanowires, nanoribbons, and nanoparticles. Basically, any material you can make ink, then you can use print, fabricate electronic device through printing technology. Now, why this printed electronics or technology is very popular? Now, if you see, this is data from IDTech. This is an independent company that forecasts what will be the market of emerging technologies, and they also do for the printed electronics. Now, if you see at 2010, the printed electronics was only 2 billion market. Then in 2015, it is roughly around 13.1 billion. Now, if you see 2020, this is 55.1 billion market. And by 2030, according to IDTech, that will become 2030, that will become $340 billion industry. And these are the major shareholder. If you look at that display means your mobile phone display, even your LED TV or OLED TV. Now you see QLED TVs, and it has a major market share. Photovoltaics, solar cells, they have a major market share. And there are other as well. There are conductor ink only for PCBs, then sensor is 2.9. And these are basically logic and memory. There are also printed logic and memory, that is 12.7% of the total market. Now, if you see that, it's a very rapidly growing industry. Now, if you look at the only printed sensors, if you see this green, that is fully organic. This color is organic hybrid. Quantum dot hybrid, this is a new technology, quantum dots. Piezoresistive, piezoelectric, metal oxide, electrochemical. Now, if you see on the left side, that is under research and development phase. Extreme right, that is basically mature technology. Now this is becoming decline or obsolete. But this is all for the printed technologies, through printed technology. Now, if you see, that is even X-ray detection, biometric authentication, and all other type of sensors, image sensor, pressure sensor, gas sensor, strain sensors, ITO, that is that is conductive material but with a transparent properties, transparent current films, temperature, biosensor, wearable electrodes. So these are either in research phase or they are going to be launched soon and the market launch phase. And some are already under growth. They are already available in the market and you can find easily the printed sensors. Now, in 2020, the biosensor has a largest share, excluding the glucose strip. If you include the glucose strip, it will become a very large market. And other type of sensors is also, if you can see that gas sensor is some share, and we have capacitive sensor, that is your touch screen is again operate on the capacitive sensor. You have piezoresistive, piezoelectric. So these are the different type of sensors market uh, currently in 2020. Now there is a growth, expected growth. Gas sensor, if you see humidity sensor, it will grow more as compared in between 2015 to 2025. So you will see 70% growth in next 5 years as well. And these are the different predicted growth from 2015 to 2025 in different type of sensor. Currently, it's a $3.6 billion market, but in 2025, that will become $8 billion market, the printed sensors. Only we are talking about sensors. Now, what is the difference between the traditional electronics and printed electronics? Now, if you see that, why there's a huge market growth of printed sensor. Now, because the traditional electronics, they are made in batches, and you need a clean room. And believe me, some clean room are very much cleaner. They are even cleaner than the operation theaters. For the printed electronics, you don't need clean room, and you can have batch process or you can have roll to roll process, like you're printing some newspaper, or maybe a long, very long. If you see that the big roll of cloth is being printed, but the traditional electronic device, they are fast operated, whereas the printed electronic device, they are slow operated. Means uh, printed electronic device, they operate in megahertz range maximum, but the traditional electronic devices, they operate gigahertz in some also terahertz. That's a drawback of printed electronics. Means the device is slow, but they are cheap. Now, for the traditional electronics, you have to do layer by layer. You need a furnace, you need a vacuum, or you need to do a crystal growth. Whereas in printed electronics, you can do layer by layer printing, normal pressure, or in vacuum as well. The advantage of traditional electronics, it's a high resolution, but printed electronics is low resolution. But again, some printing technologies that is in experimental stage, they have a high resolution. I will discuss on that also. Uh, Traditional electronics is expensive process. It's a cheap process because you need only this printing setup. But for traditional electronics, you need a clean room. You need a high vacuum. You need some high energy processes like CVD, PVD, and other processes. So it's expensive process, and you have a limitation on the rigid silicon wafer or glass. You can only fabricate electronic device on rigid wafer or glass, but in printed electronics, you can use paper, plastic, even clothes. Now, devices are small. For printed electronics, devices can be small or large. Traditional electronics cannot be transparent, whereas printed electronics can be transparent. By next 10 years, maybe you will see the transparent mobile phone as well, or even your TV will be a transparent, or even if you have your ordinary window will have some transparent, some electronic device on that, and it will be transparent. Traditional electronics is established technology. It's a very old technology. It's established, but printed electronics is an early stage technology. So it's a cohesive industry. Means the application is very limited, but for the printed electronics, it's a very diverse industry. You can, from previous example, you can see you have a e-textile as well. You have a sensors, you have a display, and it's a very diverse industry. Now, uh, now if we compare the printing technology, so that printing technology we can divide into two categories. One is contact printing, the other one is non-contact printing. Contact printing means in which your substrate is contact with the deposited device. For example, if you see this graver printing that is in contact with the substrate, or in screen printing, The screen is in contact with the substrate. In non-contact, the tool is not in contact with the substrate, only you deposit the material. Now, these are the comparison of different technologies, means for inkjet printing, uh, you have low viscosity ink. Uh, it has some drawback, it has some positive points, but the main thing is if you see inkjet printing, you have very high design flexibility. Now, if you look at the other technology, so you have a screen, you cannot change screen, obviously. For one pattern, for other pattern, you have to make different screen. Similarly, for roller, means those have a hard tooling. That tool is made, you cannot modify the tool. Whereas inkjet printing, you can give any design and you can print it. Now, contact printing and non-contact printing both have advantages and disadvantages, but the advantage of non-contact printing is basically it's a cost-effective, easy operation and flexibility. As a non-contact means it will not damage the substrate, and the material is directly applied to the substrate. And I will discuss on this non-contact printing in my talk for the printing technology. But the contact technology, that flexographic, gravure, offset, or screen printing, that is a common printing technology used for the printed electronics. Now, for the non-contact printing, the common is you can see that is fused filament fabrication, also 3D printing. It has some plus point or some negative point. There's a flexibility medium, means the stretchability of printed element is not that much. Usually thermoplastic or composite material are deposited, and dimension is 50 to 500 micrometer. Now this is aerosol printing technology is a relatively new technology. Uh, it has some limitation as shown, and the feature size can be 10 micrometer to 250 micrometer. The normal inkjet printing, I will discuss later on that also. It can be thermal printer or piezoelectric printer. And it's a very, this inkjet printing technology, thermal or piezo based, that's the most established printing technology available in the market. Now, there is a direct ink writing, DIW. You have an ink, you have a nozzle, and you push it with a compressed air, and you can print on the substrate. And you can have 250 nanometer to 100 micrometer size, feature size. And there's electrohydrodynamic printing. That is a relatively new technology. I will discuss on that also. These last two technology I will discuss, and it has a it can print high viscosity liquid, polymer, nanoparticle inks, and you can have a few nanometer to micrometer dimension feature. So next I will discuss on these two technology and what we are doing research at GIK Institute usually. Now, if you see this, it's a very simple process. You have a nozzle, syringe barrel with nozzle, and with that syringe barrel is filled with the material. You have some compressor, pressure regulator, and you push the material through nozzle. As shown, as seen over here, the video. I hope this is visible. You can see this is extrusion printing, and the material is carbon, conductive carbon. So initially we started at GIK Institute on 3 CNC machine. That is a CNC machine, a milling machine. We modify it and we use for the printing. Now we have our standalone system. We develop our standalone system with PC, camera, and other controller, and we are doing printing of the electronic device. We usually mostly sensor in here at GIK Institute. And obviously that is that it's not like that you put a material and you start printing. It has some flaws as well. So you have to control different parameters. So pressure, the feed rate, and the standoff distance, that is distance between the nozzle and the substrate. And there are many defects you have to see. There can be a bodging effects, there can be a narrow effect, or maybe a zigzag effect. So it's not like you put a material and you simply start printing. So you have to do a lot of experimentation and research to print proper or acceptable patterns or structure. These are some examples we printed. Now you can see that there is different shape showing the flexibility of the printing process. Okay. And if you see that on the right hand side, we printed on a PET. It's a simply PET sheet, that overhead printer, sorry, projector. Uh, and when we were student, we don't have that projector. At that time, we have a slide, plastic sheet, and it put on the overhead projector. So this is printed on that plastic sheet overhead projector. Now you can see that it's a flexible and bendable structure. And basically, we print a flex sensor. A flex sensor is used to monitor how much how much the structure is bent, the bending, and it can also use in the robotics as well and other application as well. Means it can give you a feedback system that by bending it, the resistance change, and feedback, you can find how much bending angle is there. So we printed this flex sensor. So this 250 micrometer is the width of the pattern, and this is 5 centimeter of dimension. And we put on 3 loops or 5 loops depending on the application, and we build this rig to test it, and at different bending angle we characterize it, and this giving us a bending angle and with the pattern width and the loops. So if it's a resistance is 5 kilo ohm or 6 kilo ohm, means the bending angle will be 40 if you look at this 530 micrometer 3 loops structure. So it's a flex sensor used to measure the bending angle. And we also do the endurance test by giving the bending incremental and discremental. Means we bended it clockwise direction and counterclockwise direction, and did the multiple time, and the behavior does not change. So we also did the endurance test, and we published this research. Now, this is a strain sensor. Now, if you see previously it was 5 centimeter, we reduced the size. The sensor area is 5.5 centimeter, whereas the total length is 1 centimeter. And we print on different material, on PET as well as on polyimide. And if you see this, we put this strain sensor on this sample, and we test it on this rig, bending test. And if you see, that is a linear response, and the microstrain and the change in resistance, how the strain sensors work on that principle. So it gave us a good result. And then what we did, we take aluminum sample and directly print the strain sensor on that aluminum piece, and we put in on tensile testing machine. Bottom figure on the left side, that the graph is shown from the machine, this tensile testing machine, and on the right side that is showing the behavior of our sensor. Means till fracture, it gives us the value. Now, then we put that was a previously or carbon based. So when there's a change in temperature, there's a change in resistance as well. So in order to have a temperature compensation, we mix two material, carbon and silver. One is a negative coefficient, thermal coefficient expansion, and another is a positive. And we make a hybrid material, and we print it and we test it. So with change in temperature, the behavior is, if you can see, that is almost linear, and the difference is not that much. Nowadays, we are working on the printed thermoelectric generators. Basically, we have a silver, and this is again polymer, organic polymer, P.PSS, and this is a thermoelectric generator. So on the tip, there's a hot temperature. On the back side is a cold temperature. Due to change in temperature, the electron flow. And this we directly print on the window. And since the window is outside, outside, So due to sun, there's a change in temperature and we get the voltage. And this is showing the behavior. So nanowatt power, and with the temperature difference, so the voltage, the power we're getting, electric power for the change in temperature, thermoelectric generator we printed, and we are now extending. This is a single cell. Now we are printing the multiple cell, and we are printing on the glass through this direct ink writing technology. Now there are another application uh, uh, of direct ink writing. This is printing of antenna on a confocal surface. Your smartphone antenna, on your smartphone, the antenna is printed through this direct ink writing technology. This is a bioprinting, artificial ear. This is being printed, and this is with embedded electronics, the artificial ear. So bioprinting or tissue printing is also done through this direct ink writing technology. Organ printing. Nowadays, there is huge research is working on the organ printing. This is cement printing, civil structures being printed. Now, there is an interesting example of extrusion printing. This is Harvard University. This is a multi-material extrusion printing. Now, if I extend forward it, now if you see that it's printing a 3D structure, and it's being printing two different materials. One is rigid, one is flexible. Now, this printed structure, if you apply some air and with some sequence, it can carry a load. Now, this field is known as soft robotics. Now, this printing technology is widely used in soft robotics. It's a new emerging field, the soft robotics. It can be operated through pneumatic, it can be electrically actuated robots, but they are usually inspired through a biomimic. They are a biomimic inspired by nature, and it's emerging technology that is biorobotics. Now, another technology that we have, uh, inkjet printing. Okay. Now, as I discussed, that this inkjet printing can be divided into two: continuous or drop on demand. Like for example, continuous, you have a continuous ejection of the liquid, and then you with electric charge you break into the droplets. It's a very fast uh, technology. On drop in demand, for example, this piezo or thermoelectric. So you have a piezo element. When you give the voltage, it will deflect and it will change the volume. By changing the volume, the liquid is ejected from the nozzle. For thermal, you give a heat, a high heat pulse, the solvent evaporate and it ejected. Now, these piezoelectric and thermal electric drop-on-demand printing or this continuous printing is commercially used technology, and it's a very mature technology, but it has some limitation because the droplet size cannot be go less than 10 micrometer. So when it drop on the substrate, the pattern size is 20 micrometer or higher. Since it's a moving part, so it's a mechanical problem. Means by movement or this thermal, it become hot and it has a thermal problem. Now, in order to generate smaller droplet, you need high energy. Another issue is nozzle clogging. And you cannot use highly viscous material, means you cannot use, let's suppose you have a ink with a nanoparticle, but you cannot increase the quantity of nanoparticle on that. So there is emerging technology still under experimental, that is electrohydrodynamic. And the next section will be on that technology. So what is it? It's very simple technology. You have an ink in a nozzle. When you apply voltage, there is a charge on the meniscus or on the tip of the liquid. when you increase the charge, it break into jet. So as shown over here, this video. So this video is when we apply DC voltage, initially it's a dripping, and further increasing the voltage, it becomes a stable. Now, this stable is known as cone jet mode. Means if you look at this, so there are different mode when you apply voltage, DC volt, it will drip. First it will drip, then it will micro dipping, spindle, pulsating jet, and then it will have a cone jet. And further increase in voltage, it will become multi-jet as shown over here. Now, what is the physics behind it? So it's basically surface tension force is holding the liquid, but when we put electric field, so the Coulomb charge force, they counter it, and then the liquid start flowing. So when you put DC volt, so you will have stable jet, single jet. But when you give in DC, sorry, pulse voltage, so this become even base, means it will drop by drop. Now, if you see this nozzle size is almost 400 micrometer. But when you see the drop of jet, that is less than 10 micrometer. Means with the larger nozzle diameter, you can have a small material or jet. So that's the advantage of electrohydrodynamic technology. There is no moving part. Only you apply voltage. And this voltage is depending on the nozzle size. It can be from a few hundred volt till 5 kilovolt. But you need a very low current. The current is in microampere range. Now, the advantage, if you can see, this is 410 micrometer, and if you see the jet size, it's very small jet size. And you can use as a spray deposition as well. So these are a few examples that I've some research. This is droplet size less than 5 micrometer, and this is a pattern of copper. This is a silver less than 10 micrometer, and if you see this nozzle is 30 micrometer, and you see this droplet that is less than 30 micrometer. So that's the main advantage of, and you can use high viscous ink, means you can even use print the you can do printing through paste as well. Now in GIK Institute, we have initially we started with this EHD printing on this CNC machine. We put it in and we start printing, and this is a P.PSS printing on a normal photo paper. Then the same setup for direct ink writing, we modify it and we put a high voltage amplifier in it and function generator, and we're doing the EHD printing through that. And this is an underdeveloped system under HEC and NURP project, and we are establishing a large, small lab scale proper EHD printing setup. These are resistive printed through printing through EHD printing at GIK Institute, and we did some characterization. We monitor the temperature and strain as well. This is a resistive sensor, and on the different type of paper. This is on the paper as well as on the plastic substrate. Then we print a humidity sensor, Mender type electrode. In between we have a black material. This is P.PSS, and these two silver are your basically your color is silver, and it is on the paper. And this change in humidity is sensed through change in capacitance, and you can see that from 50 to 15 above, we detect the change in humidity, the relative humidity, and this is showing the response time, humidification and dehumidification. And this is a schematic of the test we perform. These are few examples that the research we conducted and further doing the work. This is a printed memory, resistive memory, also known as memristor. Basic structure: you have bottom electrode, top electrode, in between you have metal oxide, and you can print it and it behave as a resistive memory. And this is a printing on the silicon substrate as well. Now The CHD printing is still under experimental stage, but it's a lot of potential for high resolution printing. These are some research from other group, and if you see that the pattern size is in the sub-micron level, means it's less than, is in the nanometer range. This is a 3D printed structure through EHD printing. On the bottom left, on the top right, this is a gold printed grid, and it's a transparent, and it will change, and it will be applicable for the mobile phone for touchscreen. And on the bottom right, that is a tiniest image printed through EHD printing. Now, the, this image size is 800 micrometer by 115 micrometer, this whole image size. And the total area is 0.0092 millimeter square. It's even smaller. The width is smaller than your hair, almost. And if you talk about the resolution, that image is 25,000 dot per inch. And they develop a special microscope to see this picture because it's made up of quantum dots. So according to Guinness Book of the World Record, this is a tiniest inkjet printed image, and it was done on the EHD printing technology and by ETS Zurich. So now, if I conclude, so inkjet printing, that is a truly additive process because it's a flexible process for printed electronics, and you can print multiple devices. No hot tooling required. For example, in case of gravure printing or screen printing, you need to have a screen or gravure roll on which you have a hard tooling, means you don't have any flexibility. It's a non-contact process, flexible process, and you can print on the variety of substrate. As you can see, we did on the paper, we did on the plastic, we did on the glass as well. And it's a low operational cost. And no clean room requirement. But there are a few challenges as well. First challenge for any inkjet printing technology, even any printed electronics technology, is ink formulation. So you have to adjust the viscosity, surface tension, and evaporation rate of that ink containing the material. Stability means that ink become amalgamated or it becomes settled, it blocks the nozzle, and other issues are related to this printing technology. Then substrate quality, that you have to control the substrate surface energy and roughness. And the other thing is that you have a printed device, it has made of multiple layers. So that layer to layer registration means the first layer and second layer should be at precise place. So that registration in printing technology is very important. So that is another challenge. And jetting reliability for inkjet printing. So the jetting should be reliable, means whenever you require it and wherever you require it, it gives you the same pattern size, means the drop size should be same. And the process and solvent compatibility means you print one layer and you put another layer. Sometimes the solvent attacks the previous layer. We call it that known as solvent attack process. So that must be compatible. Okay. Printed electronics, that the Pakistan or any developed country must look into this. We shouldn't miss this bus because we did miss the previous bus that was a microelectronic or traditional electronics. In Pakistan, currently there is no private sector working on a chip manufacturing, and PCB they are doing, but not on the chip manufacturing or device fabrication level. A few government organizations they are working, but not that much. Then it's a 340 billion market 2030. It's a huge market expected. So if even we get 0.5% share, it's a huge for us. And the next industrial revolution is Industry 4.0, that is known as IoT, Internet of Things. Printed devices nowadays are widely used in this IoT. In IoT. because these devices has to communicate, are flexible to communicate, and it has built-in antenna, and it provides you real-time uh, data, and it's a cheap. The main thing is it's a cheap as compared to silicon device. So it's a huge application uh, and currently being used in the industry, low cost technology. And since we are a textile sector, now future textile will be a smart textile or e-textile. But since we are missing this opportunity, so most probably our textile sector will also get into trouble due to this if we don't look at this printing technology. And since we are agriculture country, so sensor for agriculture and food application, we can enhance our capability if we have a low cost, cheap sensor for monitoring humidity, soil quality, water quality, gases or something or similar application. So it can enhance our productivity as well. So by this, I will finish my talk. Uh, Currently, we have underdeveloped system, electrodynamic, through NURP project, HEC, and we are working on direct printing technology, printed, and also EHD printing. So focus is currently on printed sensors, printed memories, and also printed energy harvesting device. So thank you very much, and open for question. Any question?
Thank you very much, sir. That was indeed a very educational session. Now, for the Q&A session, if anyone would like to just raise your hand, and the host will unmute your mic. Okay, host, we have someone, Muhammad Asad. Can you please unmute him?
Assalamu alaikum.
Ji walaikum salam.
Uh, it is indeed a great session. I want to ask a couple of questions to you, sir. Sir, basically, my background is from computer science. I recently graduated from University of Karachi, but my interest lie in electronic sides of IoT, making this kind of cool stuff. So I want to switch it in electronics. So my question is that, so which area is best for me to go for masters in electronics, or if I try in Pakistan, so which university should I target for research work?
Okay, for electronics, like nowadays, the control system or embedded systems, especially for IoT, uh, device integration, that's a hot topic. If you talk about for the electronics side these days, and for Pakistan, for the electronics, LUMS is a good option if you get scholarship in LUMS and do masters from there. They have a good labs there. And then I don't know about the Karachi, but LUMS is a good option. GIK Institute, they are working on the networking as well and other application as well on the in the electronics field. And also, maybe there is a CASE, Center of Advanced Science and Engineering in Islamabad. Their master's program is also good. NUST is also has a good program, but I'm not talking about Pakistan Naval Engineering College setup. I'm talking about their main Islamabad setup. And I don't know about Karachi, to be very honest.
Okay, anyone else? Raise your hand, and the host will unmute your mic. Host, are there any questions in the chat?
No, there's no question in the chat.
Okay, if anyone,
Mohammad Asad Khan.
Second thing I want to ask that if I want to switch my career to printed electronics, like wearables, so which country should I target for scholarship? Actually, my GPA is very good, and I have done some projects in electronics devices and won many competition in Pakistan. So I want to uh, uh, make my career in this field, so that's why I'm asking this question. So which country should I target for uh, this kind of research projects, and which country is best in this area?
Okay. Okay. Currently, on textile, smart textile. If you talk about smart textile, Europe, Germany, Finland, and also in UK. They are working on this smart textile. They have a huge research centers or with affiliated with the university. They are working on that, and also in smart textile, some Korean university they are working on that in Japanese, uh, and obviously North America, United States mostly. These countries they are working on the smart textile a lot. Even printing technology, the major research focus is in states, Europe, especially in Europe, Germany, Finland, Netherlands, and UK, and if in Asia, usually Far East countries, Korea, Japan, and China. So those are the countries they are actively working on this printed electronics technology, uh, and also a smart textile.
okay. Are there any more questions in the chat post?
There is no question in the chat.
Okay. Seems that okay. Therefore, we will proceed now towards the ending of our webinar. And sir, before that, we would like to present a little something. Host, can you please share the screen? So this is a small token of appreciation, given the circumstances. If this would have been, we would definitely but love to give you this in a physical form. Is Dr. Khalid with us, sir? Okay. Now, as on behalf of all our participants and our entire organizing body, we would like to thank you humbly for joining us today and giving us your time. It was an honor for us. Thank you very much.
Ah, thank you very much.
Uh,
Sorry, my mic was muted,
no
and
problem, sir.
it was controlled by actually it was muted by host, so I cannot unmute it.
Okay, okay.
So again, thank you very much.
Yes, sir.
Okay, it's a very nice.
Yes, sir.
Thank you very much for this informative webinar, sir.
And definitely, everyone, thank you on behalf of all our participants and entire organizing body. Once again, we would like to thank you humbly for joining us today and giving us your time. It was an honor for us, and thank you so much. We would like to thank our participants who have joined us today, showed interest in our events, particularly those who have joined us from Qatar. And thank you much for your continued support. As we explained before, we will share a quiz link with you all, and you will be eligible for your certificates after attempting. The recording of this event will also be provided. Thank you once again, and goodbye for now. Allah Hafiz.
Allah Hafiz. Thank you very much. Thank you for organizing.